So, second chapter of the first section. It's about bonds. Does happen in chemistry a fair amount. Comes from the concept of molecules where atoms are stuck to each other. They are bound together, and the bindings are called bonds. They could have called them bindings. They could have called them, I don't know about bound. And there's a number of different types, only really 3 of which are critical in living systems. Metallic bonds are interesting if you're running wiring, but you don't find metallic bonds or some other kinds of bonds in living systems. In atoms that easily ionize, first 2 columns, the 7th column, positive ions, negative ions. An electron lost, a proton unbalanced, positive. An electron gained, an extra negative charge. Remember, opposite charges attract one another? Well, those ions will stick to one another, positive to negative. Now, a lot of times when you go to look at descriptions of these things, you get something that looks like this. Here's a sodium atom, here's a chlorine atom. Electron goes from the sodium over to the chlorine, produces a positive ion and a negative ion. The thing is, at some point, there were sodium radicals. At some point, there are chlorine radicals. You can produce them if you're making bleach. But they're not stable. That's not the way that the world works, is that most of the sodium you're going to find out, whether you're looking at Earth or in, meteorites or whatever, is already ionized. It's already a +1 ion. And most of the chlorine you're going to find is already a -1 ion. So the idea that these salt crystals, sodium chloride, form because sodium metal is swaps an electron with chlorine, no. Is that you dry up water, there's sodium ions dissolved there, there's chloride ions dissolved there, they stick to each other, they crystallize, and you wind up with a little cube of sodium chloride, of salt. I think I'm misspelling that. Neither the 2 S's nor the 1 S looks quite right to me. Remember, it's visual, as I'm not getting a good picture of what the, I know what association looks like. Yeah, 2 S's make sense then. We'll talk about this when we talk about water, but generally, ionically bonded solids are pretty doggone solid. Those things are pretty stuck together. But the way the water works, it tends to work them apart and then separate them. So things that are ionically bonded, there's only a few ionically bonded solids that you find in biological systems. You find the ions a lot, but you don't tend to find the ionic solids. Calcium carbonate is kind of an ionic solid in our bones. Back to the periodic table. Middle columns. 3, 4, 5, and 6. They don't have full outer shells, but they're too far away from getting full to easily dump off or completely steal electrons from the environment. So their stability option is generally to swap, to borrow. Give me one of yours, I'll use it while you're using it. I'll give you one of mine to use while I'm using it. So by far the most common atoms in biological materials are these 4. Hydrogen, carbon, nitrogen, and oxygen. We'll talk about this when we get into the next chapter. And this is generally, well, actually the chapter after that. Next chapter is on water. And we'll talk about how they form the structure of biological molecules. Hydrogen, with one available electron to share out, one available spot to share in, tends to form single bonds. Carbon, with 4 electrons, so 4 to share out, 4 spots to fill, can form 4 bonds with 4 other atoms. Nitrogen has 3 spots. Oxygen has 2 spots, tends to form bridges. Now it is possible for 2 atoms to share not just 1 electron from each back and forth, but to share 2 electrons, or even 3. In the atmosphere around you, you'll notice that I always write O as O2, unless there's some very bizarre reason not to. That's because the oxygen in the world mostly associates with either integrated into other molecules, or if it's out on its own, it very quickly will bond with another oxygen atom, and it will share 2 electrons with the other atom and get 2 back, a double bond. So 2 lines between the 2 oxygens. Nitrogen from column 5. Yeah. 5 electrons, 3 spots, right? The number is 8. Will, in the air around us, form a triple bond. That's a very tight bond between 2 atoms. There's a reason why the air you're breathing is almost 3/4 nitrogen, because as it's built up over billions of years, it's really difficult to get those atoms apart from one another. Is that they're very stable in that configuration. Now, it turns out nitrogen is very useful for certain purposes, and there are certain living things that can pull those nitrogens apart and then use the nitrogen in things like proteins and DNA and other things that we use nitrogen for. But it's a very tricky thing to do, and hasn't really depleted the nitrogen in the atmosphere much over a very, very long period of time. And just to get it down, something that sticks in people's heads is HONC. Those are the 4 molecules in the order of the available bonds. And it also is a nice word to stick in your head. So HONC, 1 available bond, 2 available bonds, 3 available bonds, 4 available bonds. In years past, my exams would consist of a picture. I'd draw a picture and just have blank squares where the atoms were, and then have bonds drawn between them, and you would have to fill in which atoms they were. And it was just a matter of counting. Any box with a single bond on it was a hydrogen. Any box with 2 bonds on it was an oxygen. Any box with 3 bonds on it was a nitrogen, and any box with 4 bonds on it was a carbon. Very simple. Here's the thing. The sharing isn't always equal. If you have a larger nucleus with more protons in it, with a bigger pull of positive energy, then in a shared space with a smaller atom with fewer protons, the bigger nucleus can hang on to the electrons a little bit more than the little one can. It's not equally shared. I'll spend, you take our extra electrons, 50% around you, 50% around me. No, it's a lot of times it's like, 70% around me and only 30% around you. So I've taken your electron and I'm holding on to it more than I should be, which makes where I am a little bit more negative and where you are a little less negative, a little bit more positive. Unequal sharing produces these partial charges. This can hold a slightly negative area attracted to a slightly positive area and form structure between molecules where they're not really sharing electrons. This is a lot of what makes water do what water does. When you have oxygen and 2 hydrogens, and they're not straight out like this. Carbon dioxide is a molecule straight out like this. But water is a molecule like this, where my head is the oxygen and my hands are the hydrogens. Now, the reason we call them hydrogen bonds, hydrogen's only got 1 proton. It's lending out 1 electron, but it can't hang on to it too tightly. So its electron tends to spend more time on the other atom and less time around the hydrogen. So the hydrogen winds up being slightly positively charged, my hands. The oxygen winds up being slightly negative charged, my head. And in that case, it produces what's called a bipolar molecule. Some sources, every time they talk about polarity, they seem to think that it's always bipolar. And you would think, from magnets, you got to have positive on one end and a negative on another end. But in larger, more complex molecules, you have negative areas and positive areas, and they're not necessarily relegated to opposite ends of a molecule. They're still polar, but they're not necessarily bipolar. So this is feature for H2O. Probably should be a feature of H2O. And it's incredibly important for big molecules in our system. So it'll come up again, is your proteins work because they have particular shapes. Those shapes are partly from the connections between the components, the amino acids connecting at certain angles covalently, but also these strings of amino acids have these positive areas and negative areas, these polar areas, and that tends to hold the strings in certain configurations and give the whole outside molecule certain shapes. But hydrogen bonds vary a lot in strength, depending on how unequal the sharing is, how close together the polar areas are, and so some polar molecules, things held together by polar, can fall apart pretty easily. You could take the protein albumin, and you don't have to heat it up too much to make it from a nice round molecule to kind of a flat molecule that hooks onto the ones around it, and that's what happens when you boil an egg white, is that it goes from being slimy and somewhat transparent, where all the molecules are nice little round and not really that attracted to one another, to you heat it up, the hydrogen bonds that used to hold it in that round configuration shake and pop apart, and the molecule changes shape. And in the shape change, it hooks onto other albumin molecules that kind of lock in place. The egg white isn't slimy, it's white and plasticky now. It's also going to turn out that the feature of water being able to dissolve ions from ionic solids has a lot to do with its polarity. And so there's a connection between dissolving. And it goes, help, help, I'm dissolving. And the brown one goes, but bears are insoluble. They can't dissolve in water. And he goes, well, that's easy for you to say. You're not polar. It's a white bear. It's a brown bear. It's a dad joke, really. Okay, that's it for that particular chapter. The next chapter will pick up the features of water.